For this section, we are going to explain the classification of waves according to orientation of particles. The criterion is direction of vibration of the medium particles, studying the direction of vibration of the medium particles with respect to the direction of propagation of the wave. According to this criterion, a wave could be a transverse wave or a longitudinal wave. An example of a transverse wave is the wave along a rope. An example of longitudinal wave is the sound wave. These two examples are going to be further explained in the coming slides. So waves are classified by comparing the direction of propagation of the wave to the direction of vibration of the disturbed medium particles. You can check your whole book. You can check the whole book for the figures, and if you have a soft copy of it, you can check the animation. Types of waves. Starting with the first one according to the mentioned criterion. Transverse wave. As you can see, a horizontal rope here is connected to a knob on one end and is held by the hand on the other end. When the hand makes successive flips to the rope, this rope is going to be disturbed and thus a wave propagates. What happens is that as the disturbance is produced at one end, it propagates through the whole medium towards the knob, causing the particles of the rope to vibrate. Now the direction of propagation of the wave is from the hand to the knob. So this means from the left to the right, thus it is horizontal. While for the particles of the medium, as you can see here, we marked one particle or a certain region of the rope by red in order to be able to observe its behavior. So we observe that it vibrates up and down, which means that it vibrates vertically. So now comparing the direction of propagation of the wave, which is horizontal, to the direction of vibration of the particles, which is vertical in this case, we can find that they are perpendicular. Thus, what can we conclude concerning the definition of a transverse wave? A transverse wave is a wave in which the particles of the disturbed medium vibrate perpendicularly to the direction of the wave propagation or motion. You have to memorize this definition. Now, the characteristics of a transverse wave. Vocab terms. The crest. The crest is the highest point above the equilibrium position. As you can see in this figure, the wave is represented. On the y-axis, we have the displacement of the particles with respect to the equilibrium position are studied as a function of position along the rope. So the crest is the highest point above the equilibrium position. The trough is the lowest point below the equilibrium position. Amplitude is the absolute maximum displacement of the medium's particles above or below the equilibrium position. So we marked it here, taking the absolute distance from the equilibrium position to the crest. This is the amplitude, or you can say from the equilibrium position to the trough. Amplitude is always positive. That's why I mentioned absolute maximum displacement. Now, what about the wavelength? The wavelength, which is represented by the symbol lambda, is the distance a wave travels along its path during one cycle. What do I mean by one cycle of a wave? This means that the wave has to repeat itself identically to consider it that it started a new cycle. Take for example here, starting from the origin of the orthonormal system, going upward to the crest, then downward to the yellow point on the equilibrium position downward to the trough and backward up to the red point, blue point on the equilibrium position. Now after this second blue point on the equilibrium position, the wave or the particles of the medium tend to repeat their behavior identically as the previous one. They're tending to move upward. So a whole cycle here means the whole motion that is being repeated identically. For a transverse wave, a whole cycle must include a crest and a trough. Now there are three methods to find the lambda. So as a remark, the distance between two consecutive crests or two consecutive troughs or two similar points in phase on the equilibrium position are all equal to the wavelength of a wave. So there are three ways to find the wavelength and all will give us the same value. We either measure the distance between consecutive crests, as you can see, or between consecutive troughs below, or between similar points that are in phase on the equilibrium position. What do I mean by similar points on the equilibrium position? Again, going back to the figure, starting from the origin, which is marked by blue, the particles are tending to move upwards, then downward as they reach the yellow point here on the equilibrium position. So, do these particles or do these locations or the particles at these locations, are they considered to be in phase? Actually not, because at the same time, the particle at the blue point is tending to move upward, while the particle at the yellow point is tending to move downward. They're actually out of phase, not in phase. Now, if we continue to trace the wave, we can find that the second blue point on the equilibrium position, at this point, at this position, the particles are tending to move upward, just as the first blue one at the origin. That's why I can consider that these two these two blue points are in phase and they are consecutive. Similarly, for the two yellow points represented, at these yellow points, the particles are tending to move downwards at the same time. Application. A snapshot of a wave on a string at a particular instant is represented in the figure below. So we have the variation of the amplitude y as a function of x. Indicate the type of the represented wave. Indicate, this means that there is no need to justify your answer. Using the adjacent graph, indicate the wavelength of the represented wave. So the type of the wave represented here is the transverse wave. Why? Because the particles of the medium vibrate perpendicular to the direction of propagation of the wave. Using the adjacent graph, indicate the wavelength of the represented wave. The wavelength of the represented wave, we can take either the distance between two consecutive crests, like from C to B, or between two consecutive troughs from E to A, or between 2 points in phase on the equilibrium position like OD. And in all cases, the obtained wavelength is 4 cm, and this is expected. Now give the amplitude of this wave. The amplitude is the displacement from the equilibrium position to the maximum one. So in this case, it is 2 cm. The solution of this slide of this application is going to be attached with the video. So please check it.